Hello? No? Yes? Okay, good, very good. So let me start with a few reminders. In fact, so the first part of this course was about causality, and we're to set the ground for what follows. So we're going to go to black holes very shortly, but let me just remind you a few notions which we'll be reusing, and I also like to make a few more comments about global hyperbolicity. So, well, the basic notions in causality are these sets, which is the chronological future of a set. So you can think of a point, but you can just take any set omega. So if you take a set of any set omega in your space-time, you look at all points which can be reached from starting from omega along time-like, and then plus means future directed, and of course there is an analogous notion for past directed. So this would be the chronological future of a set omega. You can think of a point, and then for a point then would be something like that for the future and the past. J, similar, but now time-like is replaced by causal curves. So time-like curves have time-like gradient. That's curves on which physical massive objects can move. Causal curves have causal gradient, so either physical massive object or physical massless objects can move on such curves. And again, past and future. Now, a spacetime is globally hyperbolic if first it contains no closed causal curves, and these elementary sets called causal diamonds, so in this case P is here, Q is here, I take it it's the causal past of Q. I intersect it with the causal future of P, I get this set here, and this set should be compact. So this global hyperbolicity plays an important role when you're trying to solve partial differential equations. In fact, it was first introduced by Leray in the 60s, I think, in a famous monograph where he just proved that linear equations have global existence. So linear wave equations have global existence and uniqueness on such manifolds. And then this is really a question about giving Cauchy data on some surface, and you want to ask yourself, you take a wave equation, scalar or tensor one, maybe with lower order terms. You ask yourself, well, does the solution exist to start with? And where does it exist? Because it's not a priori clear that it's going to exist on the whole manifold. If you took a nonlinear equation, for example, it's easy to see. If you just take an ODE, so an ODE, you can think of this as actually a one-dimensional. So R is a one-dimensional Lorentzian manifold where you only have time. So, and it's globally hyperbolic from this point of view, right? So of course, a linear ODE has solutions global on R, but if you take a nonlinear one, it doesn't have global solutions. Now it's a PDE, not an ODE, so it's more tricky. And so indeed, if the space-time is globally hyperbolic, you have global solutions. But think of this example of where you identify time. Well, suppose you want to solve this equation with some Cauchy data here. Well, if you forget this time identification, so let's just to be precise, right? So let's take the Minkowski spacetime, say R11. So two-dimensional Minkowski. And this is globally hyperbolic. So if I take any Cauchy data on t equals 0, I get a global solution of this problem. But now this space-time where I identify time periodically, it's just a quotient of this solution. So if I give myself any data here, I know that this is, or I can transport this to data in Minkowski space-time, I get global solution, then and they're unique. So whatever the data were, the solution at T2 pi is defined by this data, and there is no reason whatsoever that the solution here will be the same as what you started with. But that's what you need when you identify, right? If you say that this surface is the same as this one, then the solution you obtain here should be actually take the same values as you had here, but in general, that just will not be true, period, right? So if you have in this case, it's clear that the Cauchy problem, understood as giving initial data on t equals 0 and finding global solutions, will just badly fail. There will exist solutions which are periodic, but it's not true that for every initial data there will be a solution. On the other hand, of course, if you start with any data, there will be solutions on a set up to the identification region, right? So as long as you don't identify, you'll get a solution, right? So this global existence and uniqueness question is how big is the set where the solution lives, and is there one? And that's for globally hyperbolic spacetime this works, and if it's not globally hyperbolic, you immediately show that there are problems, right? So this is some kind the optimal condition for wave equations. By the way, so just I haven't had time to give you examples, but of course, and I think I already mentioned that t equals 0 is a Cauchy surface for in Minkowski spacetime. But it's not true that every nice space-like hypersurface will be Cauchy in Minkowski. So a nice example of something which isn't Cauchy is you take the hyperboloid. The hyperboloid that we all love because it gives us the hyperbolic geometry by inducing the metric here. So if you take this surface, so it's a nice complete Riemannian manifold with respect to its induced metric. But if you take the causal curve, which is the null ray starting from the origin and going to the future, it's never going to intersect this hyperboloid, right? So this is a very nice hypersurface, but it's not a Cauchy surface in Minkowski spacetime. Okay, there's nothing wrong with not being Cauchy, but one has to be careful, right? It's not that just you see hypersurface, it's Cauchy, period. Also, another thing is that there is this beautiful theorem by Gerhardt that globally hyperbolic is the same as exist time function, so that each level set is Cauchy. In particular, it said that globally hyperbolic is diffeomorphic to R times a surface. And because you just flow orthogonally to the level sets of this time function, and you get a diffeomorphism between your space-time and this. So it is a bit disappointing because it means that topology is boring in globally hyperbolic spacetimes. The only part of which is topologically interesting is the Cauchy surfaces, right? You can have a lot of topology here, but you don't have much Lorentzian geometry. You can think of this as being Riemannian geometry. On the other hand, the evolution problem for Einstein equations, even though the manifold is simple, the equations are complicated enough so that this is essentially a hopeless task to understand exhaustively what Einstein equations do to metrics, and that's I'm going to talk about this in my last lecture. So reminders, globally hyperbolic, Gerhardt theorem. Yes, surface is Cauchy. It means that every inextendable causal curve intersects sigma precisely once. So this is, for example, if you think about Minkowski, that's easy to see, right? You take a point here, then you take a curve which goes backwards. It has to stop. It stops for some stupid reason, and then it's not inextendable. or you can extend it, and then it has to cut t equals 0, because it stays always in this within the past solid cone described by the time causal vectors. Let me also mention how can you violate global hyperbolicity? Well, one thing is just by introducing curves which are closed, but another one, you just take Minkowski and remove a point from it, right? So just take, so we just take our Minkowski spacetime, remove this point here. Well, this is not globally hyperbolic, because if you take a light cone which starts from this point, well, it's not going to be compact, right? But the requirement was that all these causal diamonds should be compact. Now you're saying, well, how does this fit with this partial differential equations? It's very simple. If you take this manifold and remove a point, then, for example, this equation on this space-time will be the same as an equation on Minkowski, where you're going to introduce a distribution which is supported here, right? So a delta or derivatives of delta, anything like that. Because I've removed this point, then the equation doesn't see this point, right? And therefore, but if you solve this equation with different distributions, you're going to get different solutions. Right? So therefore, it's clear that removing things like that actually is a problem for uniqueness of solutions. Right? It doesn't affect existence, but it's going to be a problem for uniqueness. Good. So this is Cauchy. Right, time functions. Right, a time function is a function which is so it's path directed, right? So gradient is path directed. An example is just t in Minkowski spacetime, and the main property here it's strictly increasing along causal curves. And that's why it's useful. It's like a Lyapunov function in any kind of dynamical systems, right? It's Lyapunov functions are very useful because they're telling you what the dynamical system is going to do, and that's what time functions are good for. Okay, good. So so much for my first chapter on causality, and let's start with black holes. And let me spend a few moments discussing the Schwarzschild geometry. And many of you certainly have already seen this metric. So, there is an equivalent. Well, actually, let me write it in n dimensions, n minus 2 here. So n is the space dimension. So if you think about four-dimensional space-time, then this would be, n would be 3, and therefore this would be 1 over r here. Right? So this is dt square, and let me write it like that, dr square divided by v, being this function being v. And here you have a metric on a sphere, unit metric on canonical unit metric on n-1 sphere, right? So this would be the canonical metric on a two-sphere if you are on in dimension 4. As I said, I suspect many of you have seen this metric already, but I suspect also that many of you haven't really understood why this is a black hole or anything like that. So, and it's easy to show, so I'm going to spend next few minutes showing you that this is a black hole space-time. Actually, this itself is not a black hole, because first, this metric has a problem at r equals 0. So if you write it like that, you have to remove this. But it also has a problem, and so let me just, for simplicity, now take n equals 3. Everything works identically in higher dimensions. So then V is 1 minus 2m over R. And then, of course, when R is equal to m, then, well, first here there's a 0, which isn't good, perhaps. But what is worse that here there's infinity, right? So this is certainly not good, right? So we don't want this, right? So somehow this region R equal to m, which is supposed to be an event horizon, is actually not even in this space-time, right? So the space-time here is R not equal to 0 and R not equal to m. So you can decide whether you take R larger than 2m, or maybe you can decide whether you take R larger than smaller than 2m. In both cases, you have a Lorentzian manifold with a smooth metric. Good. So how can one make a black hole out of this? The standard way is to do something which is called, so the optimal way is to do something which is called the Kruskal-Szekeres extension. Right, good point. If V is negative, this is negative, but so therefore this is positive, but this becomes negative. So then R becomes time, essentially. And that's going to play an important role, right? So the best way is to do something called this Kruskal-Szekeres extension. And I'm not going to do this because it takes a little more time, and essentially the all ideas are the same at the end. What we're going to do is, and which is quick to do, is, so poor man, but still good enough, is to do the Eddington-Finkelstein extension. So, by the way, this Kruskal is the same Martin Kruskal, which had some, I think, important contributions in. You shouldn't do this, sorry. Which had important contributions to number theory or something like that. And he never wrote the paper. I think that John Wheeler wrote the paper for him. So, but yes, in any case, and Eddington is the Eddington from the, who was the first to measure the light bending by the sun. And so what we're going to do, so the idea here is construct a new manifold which contains both regions, which contains both. Well, actually, where R is in 0, where R runs from 0 to infinity, right? So then both the region R smaller than m will be the region larger than m, and R equal to m. And so physicists tend to say, well, you make a coordinate change. And indeed, at the end, you can think of this like that, but it's really an extension, right? So you have two different manifolds, you're gluing them together, a gluing procedure or something like that. And it's done by introducing coordinates which allow you to glue across the surface, right? But it's not really only a coordinate change, right? You make a coordinate change and extend your manifold. And so the idea then is just introduce a new coordinate. So go from coordinates TR and say theta phi, if you are in 4 dimensions, to V, which is T plus a function of R theta phi. And it turns out that you can choose this function to get rid of this singularity in the metric at R equal to m. And so we can just do this calculation right away. So if I do this, then dt, well, actually, you can get transformed by this equation. So dv is dt plus f prime dr. So I can calculate what dt is in terms of the new coordinate. So this is the new coordinate. For the moment, it's a new coordinate and nothing else, right? So, and then we'll be extending. So then this means that dt is, and I have to apologize because my v's probably look a lot like my r's, but dv minus f prime dr, and we put it in the metric. And let me just not worry about this part here. Right, so here nothing interesting happens, but the only important part is this two-dimensional part. So if you just look at star, it's going to be minus v times dt square, well, dv minus f prime dr square. And the other part doesn't change, plus dr square divided by v. Well, let's just expand. So minus v dv square. Okay, there's nothing much we can do here. There is a cross product which comes with a plus 2v dv dr and f prime. Shouldn't forget it. And if I collect the dr square terms, and that's the important part, well, there's 1 over v from here, was here, stays. And this one gives me, well, it's a minus f prime square. Okay. So how do I get rid of 1 over v? Well, I choose f prime so that this term is 0. It's a trivial thing to do and hope for the best, right? I don't know what's going to happen next, but of course, v here, 0 will stay, then we'll have to make sure that nothing wrong happens here. But we just choose this to be 0. So get a simple function equation for f. So f prime square is equal to 1 over v square. So if I take a square root, I get f prime df over dr is 1 over v, and v was 2m over r, plus minus, actually, and this is important. Well, let me choose plus here, and I keep in mind that that I can always change the sign here, right? So in other words, I can think of taking the minus as introducing a new function, u is equal t minus f, okay? So let's choose plus here. Okay, so this should be not too difficult to work out. So let's forget the minus. This is r over r minus 2m. I just want to integrate this equation so I can give you the solution, but actually this is easy to do, because if I do it like that, then I get a 1 here. This is 1 plus 2m r minus 2m. So integrating is now easy, and there's a constant of integration which is irrelevant. So f is going to be r from this one, and the log of plus 2m log. And well, normally you'd think that would be something like that. But if you're a physicist, you're thinking, well, this is wrong because r has kilometers, and what's the log of 1 kilometer? So, but you can always shift it by a constant. Right? So log, so divide by a constant, log of a product is a sum, so it's still the same Let's integrate this, and now I don't have, if mass is measured in kilometers, which we certainly do when we write this metric, right? So V has no units, so the mass better be measured in the same units as distance. Good, so this is my function. In other words, it's r plus 2m log. Right, and now, of course, normally it comes with an absolute value when you integrate the log. I mean, it could be negative, then you'll get an absolute value. So let's just think of r larger than 2m for the moment, and then we get r over 2m minus 1. So this is my function. And note that with this choice, f prime v is 1, right? Because v square for f prime square is 1, and I've taken the positive root. And that's good for this metric too. So now g is equal minus v dr squared plus 2 dv dr plus r squared d omega squared. D omega squared. And this works in other dimensions as well with a different function f. Right? So good. So that's the metric now. And now the question is, what is this Lorentzian now? I mean, of course, you have to worry. You still have a 0 in the metric, and 0 could ruin the signature. So this is certainly Riemannian. So the question is, what about this block here? Well, if I look at the matrix G mu nu, which is the usual convention that V is x0 and R is x1, then this would be, so this is, as I said, V's. My V's and my R's are kind of similar. So I get G VV will be minus V. I get a 1 for each of dVdr, right? So there's 2 of them, it's symmetric, so 1 here, and there's no dr squared terms. So, so this is in this 0, 1 sector, right? Okay, this one, this is Riemannian, so this is okay. Now the determinant of this matrix is minus 1, so this is obviously Lorentzian, right? So that is equal minus 1, so Lorentzian. So we get a smooth metric, no matter what R is, for all R larger than 0. Now, I still have a problem at R equals 0, and at R equals 0 is a real problem, but now this metric, which I was defined only for R larger than 2m, you just say, well, what prevents me to write this metric for all R positive, right? And that's how you patch together now the surface R equal to m and the other one. Now, this equation only made sense here, right? So this is really an extension. Right? You start with this metric. It's only defined a priori for R larger than 2m, but then you say, well, let's extend it. I didn't say this, but this is a solution of the vacuum Einstein equations. The extension must also be a solution of the vacuum Einstein equations for a very simple reason, that this metric is real analytic. Right? So it's 0 for R larger than 2m, so it's going to continue to be 0 for smaller 2m as well. So it's still vacuum. And now, so the claim is that R equal to m is an event horizon, is a future event horizon, in the sense that causal curves are future directed, can enter this region, but they cannot get out. Well, this region, which is R smaller than 2m, but cannot get out. So the way to think about this space-time is the following. We have this nice spherically symmetric metric, and we think of this describing an isolated spherically symmetric object. Maybe a star, maybe something else, and the something else is this black hole geometry now, right? And so this is for r larger than 2m, if you go with r to infinity, then this term goes to 0. You're as good as in Minkowski spacetime. So this is something which is called an asymptotically flat metric. And so this is the region where we live, right? We are in a region where things are nearly Minkowskian. This is the exterior of this object. So this is our world. And now, so we have causal curves in our world. And now can we, what happens if we start in our region, go through this surface r equal to m? Well, will not be able to come back as a physical object, right? So that's what event horizon is. Good, and I mean the proof of this is very simple. First, we have to decide what means to be future directed, right? Proof. So first, future directed. And future directed is the usual case. Well, for large distances, we are in almost in Minkowski. We've decided that t increases to the future, right? So t dot positive on causal curves far away. And actually, when you want to talk about time orientation, it's really sufficient to take one curve at every point, right? Through every point, because it's only to make the distinction between two sets. Once you have one vector, which is time-like, it decides about all vectors, right? So you don't even need all causal curves, but you can just take the ones which are at rest. So for example, if you just take a curve, t goes to t, and then the remaining coordinates constant. Right, so at large distances, the metric is also looks like Minkowski, so it's obviously going to be a time-like curve, and so that's determining the orientation. Good. So now let's look at the condition. So in this metric, so let's take a curve S goes to V of S, R of S, theta phi of S. And so this is our curve gamma. And gamma dot is, well, you put dots all over the place. And the question is when gamma dot is time-like. Okay, well, it just needs to take a g of gamma dot, right? Good. So we have minus v dv over ds square from this term. Well, here we have 2 v dot r dot. Let me just put dots because otherwise it's going to be too messy. Okay. Plus 2 v dot r dot. And here we get plus r square. Well, something which is positive. So I don't need to write it down. And this should be smaller than 0, right? So this is a time-like curve. So now this is smaller than 0. This is positive. So this has obviously to be smaller than 0 as well, right? So this should be smaller than 0. So we write, well, here we can factor out v dot minus v dot plus 2r dot. plus something positive. And this has to be strictly smaller than 0. Smaller than 0. Good. So if this has to be smaller than 0, then it cannot change sign in part. It can never be 0, but it's a product. So in particular, V dot cannot be 0. Good. So either it's positive or negative. No? Positive or negative will depend upon the orientation, what is the right orientation now to choose. And we've already said what the orientation is in the far region. So when we have the orientation in far region, it propagates. If it does propagate, it's unique. Right? There's no question about it. So in the far region, V was T plus F. So if I take a curve so that R is constant, is R0, then V dot is just T dot. Right? So I have a causal curve at constant R, then this should be positive in the large region. Right? But this means, therefore, that V dot is positive for all causal curves, for all time-like curves. But then this means that I can reparameterize, well, maybe I shouldn't reparameterize this, but so now this product is negative, this is positive, so minus V dot plus 2R dot is positive or negative now? Negative, right? Right, because the whole thing has to be negative, this is positive, this has to be negative, this is positive, this has to be negative, all right? Good. Good. But now, if I'm in R smaller than 2m, so I have a curve which crosses from the exterior region to the interior one. Well, this is already decided positive anyway. Now V was 1 minus, well, V changes sign at, right, changes signs at R equal to M. So it's R minus 2M over R. And if R is smaller than 2M, this is negative, right? So this is negative. But then this is positive. But the whole thing has to be negative. This has to be negative. Right? And that's the end of the story. If a causal curve, which is future directed, enters from outside to inside, it cannot exit anymore because R can only decrease on this curve. That's the proof of the fact that R equal to M is an event horizon in this sense that I've described here. So take a curve, enters this region, cannot exit anymore. Good. So this is why the Schwarzschild manifold, well, the extended Schwarzschild manifold describes a black hole. And this is what an event horizon is. Now, this is a black hole story. But now remember this U here, right? What would happen with my calculations if rather taking V is equal T plus F, I'm going to take U equal T minus F. So same function F, but change the sign. Now remember that the solution was, this equation didn't care about the sign, right? So if I go to my calculations, right? So this still vanishes. Now, if I go, so let's just do it step by step. So here I had a U, if I make a U which is minus F, then this will not change. Here in U, I'm going to change the sign. So here, I'm going to get a plus. So here, I'm going to get a U and a plus. And so here, I'm going to get a UA square, and the sign will change. And then this will be 0. So the bottom line is I still get a metric which is Lorentzian, because if I look at my end formula, the only thing that will change is the sign here. So this 1 will become a -1. So the determinant will still be -9. So that will be a perfectly well-behaved solution. So there are two possibilities here. And you think, well, this thing can be obtained from V by changing the sign of t. If you change the sign of t here, then you get minus the previous v, right? But minus previous v means that you're changing time orientation. Right? So take a time coordinate, change its sign, changing time orientation. So the whole calculation that I did, I don't have to repeat it. The same calculation applies. We get exactly the same manifold with the time orientation change, which means that what happens with this claim if you change time orientation? Well, causal curves can enter but cannot get out. Change time orientation, causal curves can leave, right, but cannot get in. And this is called a white hole. So if you do the same calculation with rather taking V but U, you're going to get another extension, which is not the same, because obviously the causal properties are different. Right? So the causal properties here are that you can exit this region, but you cannot get in. Yes? Right. So here, the original one, we started with R not equal to M, R not equal 0, and in fact, R louder than 2M, okay? So here we had T was R louder than 2M times 2 sphere, or n-1 sphere, okay? So now here, after this expansion, I still have R in V now, right? This metric doesn't depend upon V. I get R louder than 0, and I get Sn-1. And if I do the other extension, the second the Wittgenstein extension, I get again R in U times R louder than 0 out Sn-1, but it's in a different coordinate. So it's very perplexing the first time you see it, and you wonder how is it possible that we get two different things. And this is really resolved in this Kruskal-Sekares extension, which is done by similar trivial but inspired calculations, right? So I mean, it's a trivial calculation, but you had to get the idea to do it the way you do it. And then the picture is actually very simple to understand in steps. So think of the V coordinate and the R coordinate looking like that. And here is R equal to M. So this was our original region. This is the extension here. And I'm going to rotate this picture to something like that. Because this R equal to M is a null surface. It's a wasn't probably clear from what I'm saying, but somehow it has this property that there are null directions tangent to this surface. Okay, I would need to explain. Maybe that's actually easy to see, right? That if you look, the vector dv, okay, if you take the vector g of dv, then it gives us, well, from the first term minus v squared dv, from the second dr plus r squared d omega squared. So at v equal r, v equals 0, so r equal to m. at r equal to m, dr is 0. And so we get certainly g of dv is 0 at r equal to m, right? Because g of dv will, well, this is gone anyway. This doesn't see dv and v vanishes. But you get more, right? That that dv is orthogonal also to right. Do I care? Maybe I don't care, but g of dv, no, wait, that's all there is, right? Okay, g is orthogonal to d theta and d phi, okay? So this is dv is a null vector. It's tangent to the surface r equal to m, but it's also orthogonal to each direction of this. This is called a null hypersurface. Null hypersurface. It has null tangent directions which are orthogonal to every other direction right. So actually g of dv at r equal to m is just 0. Right. Well, pulled back to the surface, r equal to m is 0. Good. So this is a null surface. So if you want to think of this as a null surface, it's nicer to write it like that. So v goes in this way and r goes this way. And if you do the same for the u coordinate, the right thing to do is actually to rotate it the other way around. So, so the extension, therefore, is this one, right? So r. So let's say so r equal to m is going to be here. And the u coordinate, you should think of this as being an extension in this direction. Okay. So now here, then u has a wrong time orientation, so u actually goes in this direction. And maybe I should use different colors. It's going to be clearer, or maybe not. Right? So we start with this region. We first extend. Oh, you don't see these colors anyway. Let me give up the colors, right? So we start with the region r larger than 2m v, and we introduce the v and u coordinates here. Now, the v and u coordinates make only sense in the region r larger than 2m because of this formula for f, right? But then we extend in this direction, we get one extension, which is this one. And this is my black hole. I can enter the black hole, but I cannot leave it. And I do the other extension in the u coordinate. Then, well, there is an overlap where both are defined. But now here, the u coordinate extends in a different direction. And this is a region where I can leave, but I cannot enter. That's the structure. So this is the two Eddington-Finkelstein extensions. And then you're saying, well, but I still have a problem here. What do I do here? Well, you can actually, turns out that you can repeat the construction across these surfaces, and you get something which looks like that in the Kruskal-Szekeres picture, when you have R to M, that's the original spacetime. First Eddington-Finkelstein extension here, second Eddington-Finkelstein extension here. Now, if you think about this metric is probably invariant under R goes to, well, never mind. It has some symmetries so that there is another R larger than 2M region here, which is isometric to this one once you do it properly, right? So that's the global picture, and R equals 0 is something which you cannot avoid. It's a singularity, you can't get across it. Curvature blows up across this region, and so this is the Kruskal-Szekeres picture. And this Kruskal-Szekeres picture, the usual way to show it is called the Penrose diagram. This is the same picture, but you scale everything down to a finite region. So this is R equals 0, R equals 0. This is R larger than 2m. This is our region where you've compressed all our space-time R larger than 2m to just this little block. It's just a picture for the moment, right? Then this is the first Eddington-Finkelstein extension with the V coordinate. That's the other one with the U coordinate. And there is a copy, another copy of our universe, which looks like that. So that's the Schwarzschild region. The Penrose diagram for the Schwarzschild spacetime for the actually, it's called for Schwarzschild, but it really is for the Kruskal-Sekeres. Good. So this is how Schwarzschild looks like, and I'm, I think, just out of time, so I'm going to stop here. Thank you. No questions? Yes.
Does the extended metric
Right. So because I didn't want to clutter the calculations, but here when you integrate this, you get this, right? So this formula makes sense both for R larger than 2m and R smaller than 2m. And so once you've done the expansion, you can use this formula with the absolute value to go back to the original form. Right? Yeah. And the same applies for the U extension. And if you were, I was cheating. No, nobody objected to this. So let me just add the comment here that, of course, when I do the extension here and here, and do it again here and do it again here, the question is what happens with this point. You know? And it's true that this point is in there, and that's but that's one has to do it carefully to see that there is actually this point in this manifold.